Inverter.
Test.
Yes. Good evening, everyone. So thank you very much for joining for this knowledge sharing session organized by the Electrical, Electronics, Telecommunications Sectional Committee of the IESL. I am the chairman of the committee, Engineer Zara Marzuk, and I warmly welcome all of you, and including our speaker. But today, to introduce the speaker, I have a very special person joining here as well. He is also the chief organizer. Yes. Chief organizer of this event. So for that, I'll briefly introduce him. He is Engineer Kosala Udugahapattua, Principal of Ceylon Electricity Board Training Center at Piliyandara. So he's a very active person, and he's the person who was very much interested and supported us in organizing this event. So Engineer Kosala, over to you to introduce the speaker.
Thank you, Sarah. Good evening, everyone. And good evening, Dr. Ravi. This is a session. Thanks for joining on this session. And there was another session we had with CEB engineers in the same manner. Then after that, we decided to share the session with Dr. Ravi's short visit in Sri Lanka. We want to get the maximum output from him. Then, as a CB veteran engineer, he was in the Lakshapan and other power station. He's expert in this section. Then I will not mention many more, and you can see Explore and IEEE Explore and other area. Then it's better to start the thing, and thanks for joining everyone again. And I invite Dr. Ravi to start the session. Dr. Ravi is a principal engineer in PC Hydro Generation Engineering in British Columbia. And as we explain many things again about him, and we will see how we can get a resource as a resource from resource person from him. I invite you to get an interaction. This will make an interact with him and get the maximum output. Thank you. Yes, sir.
Yeah, thanks for the exaggerated introduction. Yeah, I'm trying to first of all, I have to say that although your topic says renewable in the topic, but by no means I'm a expert on renewables. I'm not an expert on renewables. Over there, we usually specialize one single field. For me, I'm specialized in protection and control and frequency stability. The stability can be divided into two parts. One is the voltage stability. So I'm specialized in frequency stability. So I do not know everything. I only know one single discipline to some extent, not everything either. So anyway, I'm trying to explain you. First of all, I want to acknowledge that some of the things are my opinions only. So don't be offended or anything if I say something about CEB or something, because sometimes those are inevitable to say. But what I meant is not to insult or anything, but I want to emphasize the point, right? Say, if I'm trying to confine my speech to a presentation to power sector. So not the electrical engineering is a huge wide area, but I'm only going to talk about power sector. Power sector in the sense like in terms of frequency stability. So I think I'm pretty sure that some of the listeners or participants are from CEB. Maybe some of you are not from CEB and maybe from outside of CEB. So if you ask opinions on CEB from 5 different people, you will get 5 different answers. If you ask for a normal layman, they will say that Umbala Kumahoru. if you ask from a normal person. If you ask for a solar person, or wind person, he will say that CB is very difficult to deal with. If you ask from CB engineer, he will say that no, we are fine. We are the best utility in the world. So that kind of a different opinion exists already. So in my speech, I'm a little bit biased because I'm an ex-CB engineer. So I'm a little bit biased, but I'm trying to take out my bias because this is a technical presentation to IESL, not for CEB. So anyway, my opinion, this is my opinion again. My opinion is like if you I forgot to mention about if you I was talking about normal people, but if you talk about experts, so if you ask for a expert who is specialized in transmission, they will say that, oh, you have problem in voltage stability or transmission system. If you ask for a person who is specialized in solar or wind, we don't actually, in Canada, we don't call them solar or wind. We call it IBR, inverter-based resources, which includes solar, wind, and any other form of DC generation, like any geothermal or anything, or everything including we call IBR. So, in my opinion, IBR is a better term to speak rather than solar or wind. So, in terms of solar and wind, like I want to stress or repeat again, because some of the listeners might be well experts in solar and wind or IBRs. I'm not an expert on IBR. So my presentation would be, like I said, although you have different opinions on CB or your power system from different people, I do have my own opinion as well. So my own opinion is you have many problems in Sri Lankan power grid. Among the many, the biggest one is frequency stability. That's my opinion, right? My opinion is not just based on opinions. I did check, I did test 5 generating stations, 4 hydro stations and 1 diesel station. I found frequency instability problems on no, not all 5, except 1. 4 of them were not tuned. 4 of them governors has problems, which needs improvements in my opinion. I'm not sure whether it's already been done or not, but at that time it was the case. So I still believe that you in Sri Lankan power grid, you do have big frequency stability problems. So that's why you could not get that much IBR penetration. In order to get IBR penetration, you need to have your primary frequency control, which is done by governors, has to be working perfectly fine. So if those governors are not working fine, you do have a limitation in IBR penetration. IBR means inverter-based resource penetration. So today I'm trying to confine my presentation first to give you some physical meaning of what I'm talking about. Not necessarily using the mathematical equation that you all have done during your university time or the college time. First, I'm attempting you to give some idea about what is the stability. So I started with, this is the same presentation I am changing. I didn't fake you by just changing the date and putting IESL there. I'm using the exact same slide, right? So I'm sorry for that if you get offended or anything, but you don't have to. Yeah, first one, I should be using my, do you have any? Do you have any? Oh, no, I should be able to do it from my computer. Don't worry. Don't worry. I'll do from here. Right. Again, presentation mode, let me share the sharing. Okay. 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 Yeah, but there should be a way of doing this way of page down and page up. Yeah, that's right. It's a little slow. Yeah. Okay. The first slide. Yeah, presentation outline. So this is what I'm going to talk today. I will go a little fast on this thing because I don't have to tell you what I'm going to tell. Or I rather just tell. The first I'm trying to, like I said, explain the stability on your day-to-day work, and then we'll try to give you a little bit of mathematical equations that you learned years ago, maybe 30 years ago. For some of them, some of you. And also how to do some stability enhancement techniques that you have to do in order to get better IBR penetration. Yeah. Go ahead. Okay, that's better, even better. Yeah, good. Thanks. Okay, then I'm going to talk about two techniques. One is called excitation limiters, that is in the exciter, or the voltage control, or AVR, whatever you say it. And the second one is the power system stabilizer. So those two are the main topics for the first part of the presentation. Second part of the presentation, I will talk about primary frequency control. So this first part of the presentation is not really primary frequency control, but to give you some idea about what is stability. So this presentation been shared in CB multiple times. So some of you who listened during my presentation times at CB, yeah, I apologize. Maybe I'm saying the exact same thing twice or three times. So first of all, we need to understand the phenomena. What is stability? What are the things that really happening? Because stability can be proven on equations very easily, but in order to understand, get some physical idea is the harder part. We all know our main prime mover power is coming from synchronous generators. So mainly our system is alternating current. That means all our machines has to rotate at the same equivalent speed. So that means we call it in synchronism. So in order to understand that, whenever you synchronize a unit whenever you have a synchronous generator has a rotating magnetic field in the rotor, which is driven by a turbine. Turbine could be gas turbine could be water turbine could be steam turbine. So regardless of the prime mover energy type, you do have a rotating magnetic field. That rotating magnetic field is the one that rotates. So whenever it rotates, so any magnet has a north and south pole. So it has a magnetic field which is rotating. Whenever the prime mover gets water or steam or gas, it is going to rotate the rotor. So while rotor is rotating, you do have a rotating magnetic field. So we call it a rotating magnetic field. So when you are connected this rotating magnetic field to another set of synchronous generators in the grid already have a rotating magnetic field in there by having the voltage there. That voltage has 60 hertz, which is if you take into a three-phase, in terms of three-phase, it is a rotating magnetic field. So that rotating magnetic field, when you connect your generator into the bus, the rotating magnetic field comes from the bus. So that rotating magnetic field that coming from the external world or the grid, which is rotating at the exact same speed with the stator magnetic field, but as opposed to each other, because and if you start to rotate, so it does rotate this way. Can you see it? Can you see the animation on your Zoom? Okay. So when it is rotating, we call it in synchronism. So now your generator, synchronous generator, is connected to the grid in a synchronous manner, or synchronous connection. We call it a synchronous connection. So so at that time, your rotor and stator magnetic fields are stator and rotor, both magnetic fields are rotating at the same synchronous speed. So that's why we call it rotating in synchronism. But if you think about this way, if you jump into the rotor, you will see, because now you are rotating with the magnetic field. So if you are rotating with the magnetic field, if you, after a while, if you close your eye and open your eye without looking at the outside, you don't feel you are rotating. You are on the rotor. So if you are on the rotor, you will see the both magnetic fields are stationary because you are rotating with the magnetic field. So that's what we learned in the school, whatever the DQ0 transformation or Park equation. So that what they do is they transfer your plane from stator plane or stator frame to rotor frame. So that's the one that we learn as DQ0 transformation and Park equation. So, like I said, since you're on top of the rotor, so both magnetic fields are stationary to each other. So whenever so that can be represented by a rotor and stator. Like I said here, like I'm showing here, the rotor and stator are connected in a magnetic coupling. It's because rotor and stator is not rigidly coupled. It's like it does has a magnetic coupling. So like a rubber band. So I have drawn here as a spring, but it is like a rubber band which can break if you rotate too fast. And so if in your screen here from the right hand side, sorry, for left hand side to you is the rotor. Right hand side means my right hand, right, when I'm facing at you. But for on your left hand side is the rotor. On your right hand side is the stator, which is the load carrying part. So if you add more loads, what will happen? So if you add loads into this thing, what will happen? Your stator get more weight, and because of that weight and the magnetic, because of the magnetic force, you kind of like retard. You go into the backside to a bit. So in order for rotor to carry this load at the same frequency, rotor needs more energy to bring it back. So that means rotor has to pull that load back. How it is done in the rotor is giving more water or more energy into this prime mover, and prime mover accelerate to a different position. Now, all what I am saying is thinking on rotor frame, right? You're on the rotor now. You're not on the stator. So that's why these are stationary. So the rotor needs more water or more energy to move to a different place, but just moving is not enough. It need to maintain that position. So it need to maintain that position, right? During my CEB presentation, I explained something in Single as well, but in this presentation, I try to refrain. I try to use the English language for the benefit of the people who could not understand, or who Single may not be their mother tongue or the prime language. So therefore, to be fair for them, I speak in English, but at the same time, when you're asking questions at the end, you can ask all your questions in Sinhalese. I can understand and speak in Sinhalese very well. Unfortunately, I could not. I'm very ashamed to say that I could not speak Tamil well, but I may understand a little bit. So anyway, so in this case, so that means you need to add more water into the turbine, more energy into the turbine, and not just add. You need to add and maintain that additional amount of energy to bring it back. If you put more weight or more load, so here it happened. If you whenever you put more load, you have more current going on the stator. That current relationship need to be maintained in force balance. So under the force balance, you need to, in order to balance that external force, you need to advance the rotor to a different place. So this angle between the stationary rotor field and stator field, we call it the power angle. So if you add more load, so you need more energy to advance to a different position. So that means so the angle between that stationary axis and the new axis is called the load angle. So if you having more current, so that means you need to advance the rotor more and more. So the angle between these two is called the power angle or load angle or delta or rotor angle. There are many different names, but all those names refers one single thing: the angle between those two vectors. Because since those has a direction and magnitude, we call them vectors. So the angle between two vectors are the power angle or load angle or whatever. So now I'm going to talk about pole stripping, and we call it, sometimes we do call it loss of synchronism. I will try to explain it in simple terms. So, like I said, so in this case, the state is carrying a reasonable load, and rotor has already advanced to about 80 degrees to give the power. So, if you add another load to this power, so what will happen is, in order to counteract this load, because it's coming back, in order to counteract, it has to move, rotor has to move forward, right? So at this point, if you add more load, what will happen is, like I do here, if you add, so now it is going to go back. But now if you advance the rotor by pushing more energy into the prime mover, it can advance, but it cannot give you more power, because its position has a upper limit of 90 degrees. So if you pass the 90 degrees, if you move beyond 90 degrees, instead of power being increased, power becomes decreased. If you remember your swing curve that you learned in your school, okay, let me just put my pointer here. I assume you can see my pointer now, right? So if you see here, whenever the angle is 90, you have the maximum power. Whenever the angle is less than 90, you are stable. You can increase or decrease the power accordingly by putting more energy into the rotor or the turbine. But if you are operating at this point, you cannot expect more power by injecting more water into the turbine. So which we call a stable limit, or the stability limit of a synchronous generator. So if you remember your university or college notes, you may remember this curve is called swing curve. The equation for this swing curve, swing curve, I believe. This equation for the swing curve is E, which is the generator voltage. VT is the terminal voltage of the outside generator, which is the grid voltage. The sine delta is the angle that I was talking about, and XD is the impedance between your rotor and the external world. So if you know, this is how you all learn this thing in the university or the college, by just referring this equation and saying that, you know, if you differentiate this equation and differentiate and make it 0, then you will get the peak or the valley, right? Because your D power divided by D delta equals 0 gives you the either the maximum or minimum. So that's how you learn in the school. Now I assume that since I explained in the physical terms, now you have a better appreciation about this power angle delta, and being operating near delta is not a good idea. So I will further explain my topic by giving you some idea about how this rotor angle responds for a power change. We all know that load or load is not a constant. Load is not a fixed megawatt. It changes all the time. It changes real time actually. It's a dynamic quantity. It's not a static quantity. So assuming that assume that, you know, you are operating over here, giving this generator, assuming that generator has 100 megawatts. So if it is operating around 20-30 megawatts, so it's very stable. It has more room to play before being unstable at 90 degrees. So if you increase your power because your frequency is dropping, then you have to increase the power, right? In order to maintain that. Remember, I mentioned about the load analogy. If your load increases, you have to accelerate the rotor to a different angle to give more power. So in this case, I'm trying to explain you a position 1 to position 2 change because of the frequency is dropping or load is increasing. So it is operating at this point, which is very stable because alpha, the load angle is about 20 degrees. And if you want to move that 20 degrees to 80 degrees, because of the load increase, your rotor angle technically should move from 20 to 80 in a straight line, but in real world, it doesn't happen because everything is like second or third order systems because you have a frequency dependent component on the load. So therefore, you do have some oscillations when you are moving from one point to other point. The reason being because the rotor and stator are not rigidly connected. If it is rigidly connected, each other will follow each other very smoothly. But since it is a rubber band, it's magnetically coupled and it's like a spring or rubber band, so it does not move at the exact same way that you expected. So this is how it is going to move. So if you take the time on the horizontal axis, sorry, vertical axis, and the angle on the horizontal axis, so you from 20 to 80 change would not happen smoothly. It does have some oscillations because of rubber band analogy. So while it is doing this change from 20 to 80, I just picked 20 and 80 for the easiness of me explaining. But it's not necessarily be 20 to 80, whatever the A to B. So when it is doing, if it passed this 90 and if it could not come back to the stable point, what will happen is instead of it coming back like this, it might fly away, which we call unstable operation. So the rotor angle, so the point here is the rotor angle increases for power increase as well as it will decrease for a power decrease. Say not just the rotor angle. There's an additional dimension to this phenomena. One is yes, rotor angle, because remember that equation I mentioned, the swing curve has a component called EVT sine delta. Yes, it does depend on sine delta because of the delta, but it also depends on E and VT. That is, E means the internal voltage of the synchronous generator. VT means the terminal voltage of the synchronous generator. Since it is EVT, assuming that if you have the full power, your swing curve will be like this one, the top one, which is E1 V1 sine delta. Assuming that for some reason, because if you have a VAR demand or the load demand, if you have increased load demand, if you don't put proper compensation into the system, if your voltage drops down to a different values, in this case, in this example, I'm going to show you if the voltage becomes 10% less, that's 0.9 per unit, right? If the voltage drops by 10%, your operating curve become the lower one that I'm showing here. So that means even for the same power, it was operating at this power angle, which is about 30. But if your voltage drops, the same power angle, same conditions, the power angle becomes about 70. So that means that power angle, number one, it does change on the load because of the actual megawatt change, as well as although the megawatt is the same, if the voltage change, again it changes. That phenomena can be easily explained because it's like I mentioned that it's like a rubber band holding the stator and rotor together. So when those two are holding each other, the rubber band, if the rubber band is weak, which is rubber band, the force between that rotor and stator, rubber band, which is dependent on the two voltages, terminal voltage and the internal excitation voltage. So that means if your voltage outside is less, so that means less magnetic coupling. The less magnetic coupling makes rotor to move further and settle at a different place than the previous place for the same megawatt, because it cannot push that much megawatt with that same angle. So in this case, I'm trying to show the exact same thing. If voltage drops from point A to point B, what will happen is your power angle changes from one position to the other position. So not only the active power balance, but the voltage also affect the stability of the system. So in my opinion, like I said, your power system has bigger problem on this phenomena than in, they do have other problems as well, but this is one of the primary problems that you have to solve first. You need to solve the bigger problem first before addressing the smaller problem. Yes, you have to address smaller problems as well. There are smaller problems, but smaller problem, it's no point of addressing smaller problems without addressing the bigger problem. You need to address the bigger problem first. In my opinion, like I said, I'm repeating again because there are lots of CB people I saw on the name list. So you do need to think about the bigger problem. You need to identify the problem first before solving it. I assume after this, after listening to this one, you will more seriously think about this part first, and especially if you listen to the next part of the presentation, which is the frequency stability, frequency control, or the primary frequency control. That's the second part. First, I'm trying to give you the basic background that is needed to understand this phenomena. So like I said, if your voltage drops, your power angle, if it goes below 90, it doesn't matter whether you have enough power in the grid, enough power in the rotor. It doesn't really matter because it has gone beyond the recovery place. So here the point is the power angle increases if voltage decrease. If voltage decrease, power angle increase. Same time, if voltage decreases, power angle increases as well. Say for an instant, if voltage increases, that means the peak of the swing curve become higher, which is above the normal one, which is giving you a smaller power angle for the same power. So electrical versus mechanical. So I assume this time you understand. I'm asking I will only ask the actual physical audience to get some feedback whether I need to explain a little bit more. I will ask from these people, but I will refrain asking from the online people because it will delay the presentation. I might not be able to cover the full presentation today. Did you understand, or do I need more explaining? Yeah, good, right? Yeah, so okay, I will keep saying then, assuming that everyone understood. I want everyone to be understood because when I at the university, I'm not the person who is sitting in the front who understood everything at the first time. I'm a backbencher, who didn't care about the lecturer or didn't listen very well during my school, my university time. So I was just a normal student. I'm not the smartest student in the class. So I was a backbencher. So I want to do the justice for the backbenchers than the front benchers, because front benchers, they don't need to tell. They will learn regardless. The backbenchers are the ones that need to be educated and addressed well, because those are the actual people who will really go and service the field, rather than the front people who understand everything. They will go out from the country, just like I'm a little different, but I didn't go for that reason, but they will move away from the country and do a PhD and stay there, right? So therefore, in our education system, we have to make sure that backbenchers understand well rather than the front row people. So that's the only one reason that sorry, not only one, that's one of the reasons that make me passionable to teach what I know in a way that backbenchers could understand. So like I said, 90 degrees, in that example, I have shown a generator with two poles, which is rotating at, I believe, 3000 RPM if it is a 50 hertz system. And in country where I'm working, we have a 60 hertz system, it's 3600. So it's applicable for most of the faster machines like gas turbines and steam turbines. Whereas in electrical, in hydros, you have more poles. So if you have two poles, it's 90 degrees, but if you have four poles, it becomes 90 divided by 2, which is 45. But in practice, there are machines in our four-pole machine. 40, it is 90 means 45. And also, we have since I'm using the exact same presentation that I'm using in Canada. In Canada, we have a generating station called Peace Canyon, which most of the people in the province knows. So I take it as an example that generator has 108 poles around the rotor to make the speed smaller. So that machine, the 100, and if you divide that 90 divided by 180 multiplied by 2, which will give you 1.67 degrees. So that means that rotor angle that I was mentioning about, the acceleration of the rotor or movement of the rotor, is not really much. It need to be rotated in very close tolerance before being unstable. So it's it has to be very close tolerant. That's my point. So here I'm trying to give you some refresh your memory about the generator capacity curve. So if you think about a synchronous generator feeding the power into the grid, the impedance between the generator and the grid, assuming it is XD. In this case, I took as an infinite grid, but actually no grid is infinite. But you can study for the purpose of easiness of explaining, you will consider it as infinite, although it is not practical. So in this case, I already explained that your active power that coming from the generator G is in a swing curve, which is a E1 V1 sine delta, like that. So if you think about the voltage Kirchhoff law, your E, which is the generating voltage, should be equal to the voltage at the terminal, and the drop is J I XD. It's like IR, right? I into XD is the voltage drop. But the reason for J is because XD is, in this case, I ignored the resistive part, so it's only inductive part. So your voltage equation can be written like that by ignoring the resistive part. So if you see this way, you will see your E, which is here, equal to V, which is the voltage at the terminal, and the voltage drop means IXD. The reason for J is because actually XD is JXD because of an inductance, right? If it is capacitor, it should be minus, but since it is inductive, JXD. So if you draw this thing in a phasor diagram, your E is the addition of V plus the drop. So the drop, assuming that your current is lagging the voltage by power factor angle, so the J means 90 degrees, right? J means 90 degrees. So the JXD should be 90 degrees to the I, which is here. And the phasor diagram becomes like that. The voltage plus drop equal to the supplied excitation voltage at the rotor. So if you multiply those numbers, and if you plot a megawatt and megahour, if I do have time, I will explain a little bit more about this. This is one of the important things that every electrical engineer should know. So if you put VI, which is the actual MVA, V into I, and it would be a half circle, right? Because VI is the limit where you cannot exceed the current on the stator. If you exceed current on the stator, it is going to heat more and more, and stator has a limitation on the current, and it will overheat and it will burn away. So therefore, for a generator, you will have a half circle like that, I'm pretty, can you hear me all right? Because when I'm making my microphone closer, I see some the volume goes up and down. I'm sorry about that, because I don't get used to speak to this microphone like that. Usually they clip me microphones on my collar, but I'll try by. But so anyway, so this is called your heating limit, because it is the, if you exceed this current, it is going to burn your synchronous generator. And if you think about this angle, the angle between megawatt and megawatt are the angle phi here, the power factor angle. You will see this triangle, and this angle are similar triangles. This triangle and this triangle are similar, because this is 5, which is because this is 90, this becomes 90 minus 5, right? Similarly here, 5, this 90, this is 90 minus 5, right? We can prove that these two triangles are similar triangles. So therefore, you will see that if you put excitation more, if you put more excitation, this light blue line become longer and it will go out. Yeah, so therefore, I'm sorry, I'm calling you. Yeah, so you will see this if excitation increase, you can increase, for the same megawatt. So this is the megawatt line. For the same megawatt, if you increase the excitation, you can make the delta smaller. But it will push this thing outside if you're operating at the end. But if you're operating somewhere here, giving more power for the same megawatt, you can make the delta smaller, which explains what I explained previously physically. Anyway, this is the, so therefore, this E cannot be, the excitation cannot be increase unlimited either, because it does has another limit called the rotor heating limit. You cannot increase the excitation beyond a certain value, because if you make it more, the rotor will take more current and rotor will get burned by overheating. So therefore, you have another line like that, with center here, with this arc, giving you the rotor heating limit. And I already explained about angle delta here. Delta equals 90 gives you the stability limit, like a straight line here. But it is the delta is equal 90 is the theoretical stability limit, but practically, like I said, because it has a swings, it has oscillations, you cannot go to exact position 90, because if you go to 90, you don't have any room to play. Any change will make you unstable. So therefore, your practical stability limit is little less than 90. So it's like that. So this dotted line make the boundary for a generator which can be operated without losing your stability from on one side, the overcurrent or the stator heating from the other side, and rotor heating from the other side. So there are three positions where there are three things that make your generator limited. One is the stator current. Second one is the rotor current. Third one is the most important thing that I mentioned is the power angle or the stability limit. So when you're operating your unit, you have to make sure that your unit has to be operated within its capability curve. We call it capability curve. But if you do not know the generator parameters, you wouldn't be able to know your generator operating limits. So in my experience, I'm not 100% sure whether the operation engineers at the system control center, they do have everything on your desk to make sure that your unit operates within the capability curve. I think they do, but if not, they have to have. So it's very important. The capability curve is very important. So like I said, I'm putting all those names which I already explained. And the one that I drawn in the previous slide, which is for a round rotor machine, for a salient pole machine, is a little different. But I'm not going to explain the salient pole machine totally because it will take too much time. Since you already know the fundamental, I assume that you can deduct that fundamental and you can trust me for this being correct, right? So it does has another thing called minimum acceleration limit or zero field current limit. It is only applicable for a salient fault generator, which makes the generators a little bit unstable or more stable because of this one. But you will see the capability curve, which is this curve, which is this curve that I'm bringing the cursor upon. You will see that that's been curtailed by stability limit as well as the minimum extraction limit. But you will see the place where it crosses Vt divided by Xd. If your Xd is small, you will see that this line become longer. If your Xd is small, this line become longer. So that means your machines with smaller Xd, you will have this minimum acceleration limit push beyond its stability limit. But what I'm trying to say here is most of the generators that I know in CB are having XD greater than 1. If XD is greater than 1, so that means you will have this curve coming towards here. Because if the XD is more, but if you make your XD less than 1, then this line will surpass this line, and this will become like it is kind of like ineffective, because you only need to worry about the thermal limit, not the stability limit. But since most of your generators in Sri Lanka having XD value of more than 1, you should be more careful. You are more on the verge of becoming unstable, because especially on the under-excitation region, not on the over-excitation region. This only happened during the under-excitation region. So, so this is one of our generators over there. It's called 7 Mile. 7 Mile means it's 7 miles to the US border. So we one of the generating station, which has a XD of 0.82, which is less than 1. So you will see that your zero field current is out of its capability limit, so that this generator can operate in this red line, within the red line, full operation range. So the generators with smaller XD values will have the better operation range. So I think the next one is the other way. So you will see another point that I want to mention. We have within our excitation systems, you have a feature called under-excitation limiter or minimum excitation limiter. So your minimum excitation limiter, in this case, the blue line, under-excitation or minimum excitation, you need to place it a little bit above the capability, so that limiter will limit the capability of the generator where it will otherwise exceed the stated current. So it's very important to set your minimum excitation limiter in such a manner that the limiting will happen before overheating or before tripping. And we do have another protection element called the loss of field protection, which is the red dotted line here. You need to make sure that that red dotted line will be below the limiter, because if limiter fails, then only should protection operate. Otherwise, protection should never, technically, protection should never operate. There should be other limiting, other measures that would have been taken before the protection. Yes, we do have protection, but protection should never operate. So that's our logo. In the place where I work, it's called BC Hydro. Our motto is protection should never operate. There should be other control measures which should prevent protection being operated, we call remedial action plans. So we do have several remedial action plans, and our protection very rarely operates. Our protection operates on under very, very extreme conditions. We kind of never heard about protection operation unless there are exceptions for sure. There are places there we go wrong and protection operates, but it's very, very rare. And if it operates, we will find why protection operated, why other preventive actions did not prevent that protection operation. So in this case, one of the preventive action is the under-excitation limiter. So like I said, smaller XD values are more stable. So here you will see that one of our generating units called GMS, Gordon M. Schramm, which in our engineering, we did a miscalculation. So what we did was, our original generator was having about 0.8 XD. What we take is in the book, somebody convert that XD into ohms. So we have given that ohmic value to the manufacturer. So when we increase our MVA, we upgraded that generator. They went with ohmic value rather than on the per unit value. So they gave us a generator which is having a XD value of 1.4. XD value of 1.4 over here. So so we ended up with having a really bad generator, which has a very limited capability curve, like this red one. And now we have to further limit that generator by introducing a under-excitation limiter, the blue line, or minimum excitation limiter, the blue line, which will handicap which will limit our operating range of that unit. So that unit cannot suppress the voltage by reducing the excitation. So we have to operate the limiters before its capability. So when you are specifying a generator, make sure that specify generators with XD less than 1 per unit, not the ohmic value. So this is an error we made. So since I am presenting this thing to our engineers, so we need to showcase our blunders, and so that the wise people should learn from others' mistakes. So this is one of the lessons learned for our other engineers, that never make that mistake. So this happens some time ago, like in early 2000. So but now thereafter we have done many rebounds, but we make sure that our XD is less than 1 thereafter. So this unit we have to live with this. There are 10 units. These are 321 megawatt units. You will see that 321 megawatt unit. 321 megawatt units. So you have 10 of similar units. So that means 3,100 megawatt plant. So we have a handicap 3,000 megawatt plant. So remember two things. The rotor and stator are magnetically coupled. And the increasing field current, or the increasing the voltage, or increasing the E, will make the rotor angle small. Same as decreasing E will make the rotor angle bigger. Remember, I showed you the swing curve. So we can use this phenomena to introduce a stabilization control for the generator, so that when generator moved from one point to the other point, it doesn't have too much oscillations or too much overshoots reaching the second point from the first point. That device is being called power system stabilizer. So the power system stabilizer, what it does is, whenever PSA sees a rotor angle increase, it will increase the excitation current by adding a modulating signal into the existing exciter, so that it will little bit boost the voltage, but we will limit it only for 10%. So 10% change in the voltage could happen at the expense of safeguarding the grid. Sorry, the safeguarding of the grid will happen at the expense of 10% variation on the voltage. But this thing doesn't happen all the time. This will only happen during the transients. So transients, it's okay to sacrifice the voltage tolerance to 10% by adding this PSS, because it's better to have 10% less, so more voltage than having no voltage. So similarly, if the PSS sees a rapid rotor angle decrease, so that means rotor is moving towards me. So therefore, at that time, we reduce the excitation. So we'll call this equipment a power system stabilizer. What it does is it adds another torque into the thing, because if it is moving away, it gives a torque to bring it back, positive or negative direction. So we call it adding a damping torque, because when you are moving one to the other one position to the other position, instead of having a huge overshoot, it will make that overshoot smaller, as well as it will damp out that overshoot quicker, rather than giving it for a long time to die. So that's why we call it damping. So how it is done? So it is only done for the static excitation system. So I know that some of the generating stations are not static; those are rotating stations. So what I said here about the power system stabilizer is not applicable for the rotating units. Rotating exciters or non-static exciters. It is only applicable for the static generators, where you feel the rotor current through slip rings. So, like, in other words, brushless is not applicable for the brushless. It's only applicable for the brush generator. So what we do is we added at this PSS, we are modulating into the summing junction to make sure that damping torque happens. How I'm doing for the time? Okay. So how long has been left already? Now, what is the time now? Nearly 1 hour. So there are 4:15. What is the time now? 4:19. Okay, yeah, it's about 1 hour. So I don't think that I have any problem in timing. We are good. So like I said, this summing junction, what we'll do is this position, because you compare the reference voltage to the terminal voltage and doing the AVR action. So since this is a summing junction, we call it summing junction. So summing junction is the one that takes the PSS, and on top of the reference voltage of 1 per unit or 1.2, whatever the voltage that you set, you will have an additional control which is superimposed into the existing reference voltage, and make sure that generator does not go unstable. So we call it modulating into the exciter. So this is one of the examples that we did in 2008. So you see that we introduced a system disturbance by giving a little voltage change here. You will see that the rotor oscillates like that and settle it down. When you are going up, again rotor oscillates the other way. Here is coming down, and here is going up, and oscillates and come back. So you'll see that after we give the exact same disturbance by adding the power system stabilizer, you'll see that the power system stabilizer stabilized or damped out the oscillations within 2 oscillations. You only have 1, 2, 1, 2, both way, going up and down. So therefore, I put this slide to explain or show or get a feeling about what you can do by adding a power system stabilizer into the system. Like I said, whenever you have more and more the IBR or inverter-based resource penetration into your grids, these are more and more important. I mean, at this point, some people, if I ask from a general public will say, most likely will say, oh, CB doesn't want solar and wind. They will blankly say it. Or instead of saying it point blankly, we have to explain them from the power system utility side of view. Utility has some cost to incur, or cost some preventive measures, or some measures that mitigate the problems that coming from IBR. So rather than just refusing IBR, we need to educate the people who are especially non-technical people about this phenomena, about the cost that the utility has to spend when we are connecting the IBR. So in Canada, whenever IBR comes, they know that there should be a cost for the utility. So we tell them you need to quantify. I'm not expert in quantifying the number, but there are different departments in our organization which will quantify how many maintenance, what is the maintenance cost, what should be the capital cost of these changes, adding PSS, all those things. They will add the number and they will say that whenever you connect us 10 megawatt plant, this is the cost to you. You have to pay this thing for each megawatt hour that you generate. So that's how we manage the opposition, or that's how we manage because the people who are coming behind IBR, they actually, I mean, they do have a good intention of putting megawatts into the system, but sometimes they undervalue the mitigative measures and cost of mitigation for the utility, and sometimes they themselves might not know about this thing. So from your side, you should, instead of you say that no, you should explain why it is no. And I mean, I think whenever, most of the time, no is not an option. You need to tell them this is the cost of us. You might need to run a synchronous generator or synchronous generator plant or static compensator. So in order to absorb that higher penetration of IBR, you need to do something. So that costs. That cost need to be reflected in the power purchase agreement. I mean, I'm only expressing my opinion, right? So I'm not political or anything. So I'm sorry if I offend somebody. So again, this is the same thing, exact same graph, but I want to see the modulating action. You will see that here, no modulating action. Here you will see that you do have the modulation action for the field current. In terms of how the PSS is implemented, I think this might be less interest to you. Now I understand. I will get some feedback from the physical audience here. Did you understand what is PSS and how important it is? So you have no idea about PSS. Yeah. Maybe if you get about 80% of what I'm saying, that's okay, because it's hard to get 100% because, like I said, as a backbencher, I know these things, experienced by myself. So how this rotor angle that I mentioned is not an angle that you can measure. It's not an angle where I said that yes, you can you can go on top of the rotor and measure the angle between two magnetic fields, but it is not an easy thing to be on the rotor. So you need rotor instrumentation if you need to determine the this power angle. But rotor instrumentation is very hard because rotor instrumentation needs to bring it back to the stationary world. So because it's rotating, you need slip rings. We call instrumentation slip rings, which we tried about 20 years ago, and it is a huge maintenance mess because you can buy instrumentation slip rings where you can install on the rotor and bring that signals into the outside stator world, but it's very expensive, very maintenance intensive, and it's not worth it. So we abandoned that idea. So you don't have to try again because you have examples that others have failed. So so those are called the delta omega type. You measure the actual frequency deviation. And the second way is the estimating the rotor speed deviations by monitoring the electrical power. We call it delta P power, delta P. If you remember the equation that I mentioned, the electrical power equals VT E sine delta divided by X. So if you know P, since it is sine delta, then whenever delta is in the smaller range, you can say that sine delta equal delta. So therefore, by measuring power, you can estimate the delta. So that's called the integral of power type or delta P type. So by measuring the power, you can estimate delta. If your power is changing, so your delta is changing. There's a relationship. We figured out that relationship, and we measure the actual power, and we use it this way. So like I said, delta omega type has various disadvantages and advantages as well. So we have delta P type and delta omega type. Delta P type is the most popular one, but we do have another one called dual input type, which is we use the advantages of delta omega and delta P both. Dual input type, that's the one that we use. So the dual input type, we have one input from the frequency, like I said, from the rotor frequency, from the rotor instrumentation, and actual megawatt. It can be measured using the transducers, high speed transducers, not with the filters, because whenever you add a filter, it will make the signals flow, and you are too late to control. So we do have some equations here because it's implemented inside the digital world. You can do digital signal processing to process the megawatt signal and extract the power angle or delta and give a corresponding PSS signal. So I'm not going to go into details in over there. I do go into the details, but here for your side, I want to give you the idea or the principles or the on the background, not everything, Like just want to stress the fundamentals. What I am doing here is stressing the fundamentals or highlighting the fundamentals. So I'm going to go a little bit faster there because it's too many details. So what you need to remember for the summary, I'll end this presentation at the end of this thing because it's like 1 hour and 20 minutes now, right? Close to. In about 10 minutes, I will end this presentation and open for the questions. So whenever the large, you already know that whenever the rotor angle is large, units are more unstable. And whenever generator is heavily loaded in the under-excitation region, that's the place where your rotor angle become biggest. So therefore, that's the area where you should avoid operating your generating unit. And the minimum excitation limiter or under excitation limiter is one of the remedial measures to prevent the rotor angle instability or the frequency instability. And also power system stabilizer, adding a power system stabilizer can greatly reduce the system or the generator being going on out of synchronism. And I think I did not add the statement saying that you need to have proper coordination between protection and the limiting in order to operate the limiter first rather than protection between the unit. So here, I mean, like, please don't be offended. For the CB people, please don't be offended. I know at CB, at my time, maybe it's different now. At my time, I'm not sure whether we do have this coordination between limiters and the protection. Yes, protection, they are doing good job by looking at the protection. Well, controls people, they do look at the control side of it to operate the unit in the voltage regulation mode, but I'm not sure that coordination happens or not between the operation. That's why we don't call it protection in busy hydro, we call protection and control, P&C. The protection and control means one department, that's my department, take care of protection and control both, and the coordination between both the protection and control. So that's the end of my slides. So for this first part of the presentation, I don't know whether we are going to have break or whether we are going to have, yeah, maybe one of you can tell them what to do or whatever. Yeah, yeah. And if you do have questions, yeah, I'm more than happy to answer. Yeah, you can do whatever.
5 minutes break. Let's have a 5-minute break and resume the presentation afterwards. Yes. Testing. We are back for the second session. So I'm handing over the controls to our esteemed resource person.
Yeah, thank you. And there was a question from the audience over here. The question was, I assume he maybe the person who is asking question, maybe I assume he's from CB or some of the IPPs. So he's asking, they do have PSS in their generator. So they're asking if you have PSS, so that does it means you can add more IBRs. No, IBR means assuming renewable. In your terms, it's renewables. In my terms, it's IBR. Yes, you can add more, but the most important thing is if you just having a PSS with typical numbers, typical parameters, because PSS is a DSP module. Over there, we instead of module, we call module. That's the American pronunciation. So sometimes I do say I try to make module, but they do have a DSP module. So but that DSP module need to be taught what to do. So you need to parameterize the DSP module, like what is the washout filter time constants, what should be the inertia of the machine, and what should be your ramping rates, how fast, what is the rate of change of megawatts when you change the set point. You need to have all that information programmed into the PSS in order for PSS to damp the oscillations the way that I shown you in the screen within one or two cycles or one or two overshoots. But if you do have any number, it may damp, but it might take 6-8 cycles to damp out. So it might be ineffective, but it does not hurt. I should say that. Don't disconnect the PSS, although you don't have the numbers. Because any numbers should work technically, but there are numbers which are critical, which may make the power system stabilizer to a destabilizer. There are places where you need to automatically turn on the PSS and turn off the PSS. Anywhere when the power is less than 10% in the machine, you should have to turn off the power system stabilizer. If you turn on the power system around 0 megawatt, whenever you synchronize into the system, it makes the incoming generator worst, because under near 0 megawatt area, your power angle act differently because you go into the negative power region, right? So therefore, it need to be turned off when you are doing. Usually, there's a feature inside the exciter saying that what is the minimum voltage where power system turns on. So you need to set that voltage into like 10% or 20%. In addition to the parameterization. So therefore, it's not a simple answer to say that, yes, I have a power system, it's fine. No, you need to tune. In order to, it's like a chicken and egg thing. Which comes first, chicken or egg? So in order to do the power system stabilizing properly, in order to properly set the power system stabilizer, you need to, all those since it is digital signal processing, DSP, you need to do it on a model. You cannot do it in the real generator. So you need to have a replica of the model on the computer on PSCAD or we use MATLAB Simulink. Some people use PSCAD. The software is immaterial if you do have the right parameters for the modeling of the generator. So if you model the generator correctly, and also you need to know the impedance between your generator and the rest of the system under worst case as well as strong case. So you need to do the PSS tuning for two cases, weak case and the strong case. And your compensation, we call it lead lag compensation. Your lead lag compensation parameters, you have two time constants for the lead filter and the lag filter. You need to set those time constants to cancel out the time constants in the system. System means generator, exciter, and the rest of the system. So you need to know, like I said, you cannot measure it just by putting an ohm meter or any other spectral meter. There are ways to measure as well, though. Don't take me wrong. You can inject a white noise and you can generate the FRA or frequency response analysis, which is, I think we don't do it because you are risking the system because you are working on a running unit. Instead, what we do is we model the unit, we model and not just model. We model the unit and verify that model. We call it model verification. We verify that our model acts the way that it is actually acting by giving a disturbance, and we'll see what model tells, and then we will do the same. We'll wait for the same disturbance and compare the results with the model results to make sure that model is actually representing the actual system. Otherwise, there's no point, right? You're going blind. It's like walking on the street with blind. So hopefully I addressed your question. I think I took a little bit more wider approach because others may have other questions. So I try to cover the broader question range because we didn't. The audience, online audience, didn't ask questions. So either they understand everything that I'm saying, or I'm doing a really poor job. They then there's zero, and they did not understand them to an extent where they didn't get the knowledge at to a point where they can ask a question. So anyway, so now we are on the second part of the. So we how long that we have until 5:15. So I will do this thing within 25 minutes, right? So it's a little bit harder to do in the 25 minutes, but I will go a little faster at the places where you don't need to have attention. Since it is presented at a CGRE, CGRE is an international organization for power systems. I'm not going to talk about that too much to save the time. So I'm going to skip this slide as well. You all know about the power systems, loads and power systems. So I think in this case, I'm going to talk about the interconnected section. This is only this part will only be applicable whenever, I don't know whenever you connected to the India, then only this is applicable because we in Canada we have an interconnected system. This is the largest ever rotating machine in the planet, the North American grid. So I will go fast. So this is one of the disturbance that happened in North American grid. I copied. I don't have the exact date. So you will see. Going to go to the cursor mode. So you will see that under normal circumstances, frequencies operating between 60 and 60.02. You see that how stable the North American frequency is, right? So remember, this is like expanded scale. The bottom is here is 59.9 and top here is 60.02. So in this case, under this disturbances where one of our generation transmission line got tripped for a lightning. For lightning is exception, right? You cannot coordinate or you cannot have remedial action for lightning. So you have to trip the line, or line will automatically get tripped. So in this case, one of our line got tripped. So you see that from this stable operating point, it became to 59.92, and you will see because of this sharp drop, you will see that all the governors in the system is not one single governor. All the governors in the units responded to address this power deficiency. All the governors in the province, not one single governor, right? I know that in CB, you will have one or two frequency control machines, whereas we don't have that case in our case. We do not have frequency control machines. We do not have frequency control. I'm repeating it. We do not have frequency control machine. Every machine in the system is operating on the exact same troop of 5%, not even 4%. Yeah, I know in Sri Lanka it's 4%. It's fair because you are having a 50 hertz signal, whereas we are having a 60 hertz signal. We got our generator is 5%. So no unit in whatsoever condition will operate at other than 5% droop. Every machine in the system will operate on 5% droop. No 2%, no less percentage. You can, I think I do have an example of different groups, but it's just for an example for the educational purposes, not actual purpose. In actually, it's all the units are on 5% group. So you'll see that the frequency drop, all the governors within the scale here is in the seconds range, within 6 to 12. So that means within 6 seconds, all the governors has responded to supply the power deficiency by adding increasing all the units megawatts, so that frequency stabilize as a different set point. So thereafter, frequency being we do have one called AGC computer, automatic generation computer control computer, which is we call secondary control. For any disturbance, we will wait until 20 seconds. We will wait until 20 seconds. After 20 seconds, if it is stabilized, then we know that there's a power deficiency. So then we use selected generating units, we call AGC units. We will send remote raise signals to those particular selected generators. Those generators being selected based on its spinning capacity, how many megawatts it can take more, as well as the water in the reservoir. So we send those raise commands remotely from the we call FVO, Fraser Valley Control Office, in your case, System Control Center. In System Control Center, we send signals to selected units to bring the frequency back to 60 hertz. You will see that it is a slow operation because you need to send that signal through microwave links and PLC carrier links, and it takes time to recover the frequency. But it is perfectly fine to operate at 59.96 for a longer time. So we operated at a lower frequency, but eventually it will be recovered in the scale 60 hertz, 60 seconds. So that means 1 minute. So after about 5 minutes, it will bring back to the normal frequency. So that's how we operate our system. So in this case, we do have another parameter to meet, not just the frequency, and we have to maintain. We sell power to California from the province that I am in. I'm in a province called British Columbia. We sell power to the United States. So we need to maintain that power flow on the tie lines. So we do have some equation for that, and we maintain that equation, and we increase our power in such a manner that we will maintain that power flow. Otherwise, we will get penalized for not sending the purchased power. So it will be applicable to you whenever you connect to India. Until then, you can forget about that part. But still, that AGC is there. You don't have to worry about this tie line power. This one, you only need to worry about PE. Again, this equation is correct. Don't need to worry about this biasing factor. So you will have area control error. You try to make this area control error 0. Area control error means, in your case, since you don't have the tie line power, and since you don't have the biasing factor, you make the frequency difference 0. So it's simple as that. So your case is very, very simple. So like I said, whenever you have the renewable integrations, IBRs, so it will add an additional burden on our governors, because they have to adjust its set point, or the AGC computer has to adjust its set points based on the frequency change. Because of that, our governors has some it take about 3 years to notice that our governors has varying band, because it's operate at the operating point too often. So therefore it wear out our mechanical components. So therefore, in order to eliminate that, what we did was we introduced deadband into the governors. So governors has a deadband. It will not rest. We call 5 millihertz deadband. So millihertz, right? Not 5 hertz, 5 millihertz deadband, which is 0.005 deadband, so that it will not react to those small variations in wind and solar. But if a big cloud comes and take off your solar, then there will be a bigger change in the frequency. Then our units will react. Reason why I'm saying is that's one of the mitigative methods that might be applicable for CB. And again, like I said, the dynamic stability concerns because of the voltage fluctuation and the power fluctuations make the power angle variations. That power angle variations, if you do not deal that power angle variations very well, it will make your machines go unstable. So here I'm trying to explain you the primary frequency control, which is the first part of that curve that I mentioned. Here again, I will go a little fast, and I'm not going to explain about all the parts in the generator. So I assume that you will know you have a synchronous generator coupled with a turbine. In this case, this is an actual turbine called reverse stroke unit number 5. Look at the size of the person. This 630 megawatt one single unit. Sorry, 600 one single unit is 630 megawatts. We have 7 of them. So this is the size of the person and the size of the generator. You can imagine the size of the unit. So the frequency control is very simple. Like I said, governors, so I'm not going to go into too much detail here. The point here is to have a set point, and you do have set point, and your speed control takes over. And I'm going to go a little fast about this thing because it's not the real point that I want to bring you today. So I will skip some slides. I did have some animations which I did for CB engineers, but since I only have about 20 minutes, right? So therefore I will skip those slides because that's not the main point. These are like basic things that you may already know, because history. And I'm going to go a little faster on this one. So there was some animations that I mentioned. I'll go faster. I'll go fast that. And I'll start from here. If you have a single machine, feeding a load, like in a hospital or in your home or in your paper mill or something, where you have one single machine, then you operate that machine in such a manner that you have a set point here and you have a speed sensor inside the diesel generator or whatever the generator, maybe a mini hydro, whatever. The mini hydro, micro hydro, it monitors the speed and it matches the set point. So regardless of your electric power demand, it will adjust the mechanical power to make sure that speed is operating on one single line. So that means your operating line is frequency versus frequency versus megawatt would be on a straight line like that. Now we call this line a isochronous operation because it's always maintains the frequency. The frequency is controlled by that particular machine. So I believe this is the way that all the system during my days, actually in 90s, this is how we operate. We make one of the generators in Victoria, Lakshapana or Kotmale, or Ranjanigala too, I think. So we make one machine to do the load balance, and it will control the frequency, basically, frequency of the grid. But in this case, I'm only referring it to a one unit feeding the load. So we do have the reason why this slide is being here, because we do have a one called non-integrated energy, where very rural areas, we do have a one single generating station feeding the load, which is operating on isochronous. So in isochronous mode, whatever if you have 100 mode, it will operate 100 megawatt, it will operate on that one, and it will be controlling the frequency. But if you have another unit coming on, if that generating station doesn't have enough, like if that load grows beyond 100, now you need to bring another unit, right? If you bring another unit, and if you put that unit also into the isochronous like that, so you have two operating lines on top of each other. Although it is called on top of each other, there's nothing called identical in this world. There will be slight differences. So one set point might be 50.0000001, and the other might be 50 or 49.999. So if you have two set points inside the governor, so those two governors will try to fight each other. One is trying to make the frequency to 59.999, so 49.999. The other one will try to maintain the frequency to 60.0001. What will happen is, the unit that has more the unit that has more power will take the precedence. The other one has to follow. Other one will be at the end, and those two will be fighting each other all the time, and there will be a frequency variation all over the time with a fixed oscillation frequency. Oscillation frequency is the one that oscillation frequency depends on the units inertia of the both units and the power of the both units. So since it is since you cannot definitely share the load in a coordinated manner, they introduced one called droop. So what they did was in technically, you take the mechanical power and you measure the mechanical power or electrical power, and you change your set point based on the power. If somebody is, so now the new unit that is coming on G2, instead of making it isochronous, it come as a droop line where its set point is automatically changed based on its load. Whenever the load is 0, you have a operating point like that, because your power is 0, your mechanical power is 0, so therefore output coming over here is 0. So that means it's working as a normal governor. So it has a set point of, in your case, 50 hertz. In our case, it's 60 hertz. So this unit, whenever you synchronize this unit to the system, the other unit will still operating at 100 megawatt. And since this one came in new with a droop operating line, since it is programmed 60 hertz at 0, it will not contribute any megawatt. It will come just like 0 megawatt, theoretically, assuming that no rough loads or no anything. So it will remain on the line. It will remain on the line with 0 megawatt, whereas the other one is feeding the 100 megawatt load. So assuming that this is not a big grid, this is a small grid with 2 generating units. So you are fine. So now the second unit came in. So assume that if your frequency further goes down, the other unit can give more power. How it is done, I will explain. So assuming that this 100 becomes 200, so what you can do is, maybe I'll go back. So when you put the unit back, it will operate on 0 megawatt. Now, if you want to add more megawatt onto this unit, what you need to do is you need to increase the set point to 60.5. If you send rest command to the set point, so this operating point becomes here, right? Like this. If you increase, so that means this line at 60 hertz, the stable operating point would be about 25 megawatts. So this unit, the second unit that you added, will be taking the load of 25 megawatt while it is doing, since this one is maintaining the frequency, it will back it off from original 100 back to 75. If you push this one again more, it will take 50% of the load, whereas this will come back to match the frequency. So this is how the frequency control happened during early days when the system is small. So when I was leaving Sri Lanka, our peak was about 700 megawatt. Now it is like 1500 or so. How much? 2000. See, so now 700. So assume even 2000. So that means it's like almost more than double, right? So therefore, in order for this smaller system, this is fine. One unit making the isochronous operation, which will take the variation of the load, whereas the other unit is a unit that take whatever the controlled load. So in this case, what will happen is the droop means the slope of this line, which is the feedback factor. If you have bigger feedback number, droop will be bigger, because this R delta P will be multiplied by R and given as frequency, right? So therefore delta P multiplied by R is given as frequency change. So this is how the equations work. I know you all know about that one. See, assuming that in this case, assuming that if when the grid is bigger, you don't have to put another unit into the isochronous mode. So this is kind of like I try to mimic the bigger system. Previously, I tried to mimic the smaller system where which is working all right with one unit in isochronous and the other units are on droop. But when the system becomes bigger, because one unit cannot fulfill the load variation, because assuming that like 2000 megawatt, you will have a 10% of 2000 is like 200 megawatt. You need to have about 500 machine to have that 200 load. But during our times, when we have 700 peak, you have 10% of 700 is 70 megawatt. One unit of Victoria would do that. Whereas now you cannot do it. But therefore, you cannot practice the typical practice that you've practiced over the years. You need to learn from other people, not by doing it and doing mistakes. You learn from others' mistakes and how other people do. I'm not complaining or anything. Don't take me wrong. I think maybe you are doing it right now the way that I explained, but I have a different impression that's not the case. You will make one machine lower droop and let it to take all the load variation, and complaining about solar penetration and the wind penetration, all the IBRs are coming, you cannot cater, the system is unstable. No, there are ways to mitigate those problems. So this is how we mitigate. So if you have a bigger system, like assuming that in this case, you are feeding 100 megawatt, your load is 100 megawatt, in your case 2000 megawatt, you have assuming that you have two units, each 50 megawatt in this case for the explanation purposes, so you are feeding a 100 megawatt load. So whenever these two group lines are on top of each other, slight variations on your set point, it really doesn't matter, because it could be on top of each other or could be a little bit apart. So in this case, stable operating point is this point. So both unit will have 50 megawatt and it will take 100 megawatt. So assuming that after a while that 100 megawatt become 150. Now, since both units are operating on this single line, it will see that frequency is dropping. So it will open its wicket gates or gas valve to add more power. And what will happen is it will open its gate automatically by the governor, from the governor, to operate at a different frequency. So the unit will, both unit will, since it is programmed on top of each other, both units will take over the additional 50 by contributing 25 and 25, and those will operate at a different frequency like that, right? I'll go back here. Both unit will operate at a lower frequency because it's been 75%. But so now your system operator, whoever AGC computer sees this unit is operating at a lower frequency more than 20 seconds. So it will look at that frequency change and it will pick, assuming that one of the unit can have more water. So it will issue a raise command to that machine, speed set point raise or the megawatt set point raise, so that it will lift the load. So whenever you press this thing, now the stable operation for these both machines, one is here and the other one is here. So that means whenever you load that, what will happen is the machine with 75 will go to 100, and whenever it is going, since it is programmed on the governor line, the other one will back it off and it will come back to original program position, original 50 megawatt. So in this case, one unit megawatt 50 and the other unit megawatt 100 will be the stable point. We are having a stable point. So therefore, in this case, for a frequency change, both units responded the system simultaneously, same time, and equally based on its capacity. So if you have a 100 megawatt machine, if you are having a 1000 megawatt machine, this will take 10 megawatts, the other one will take 100 megawatts because droop is based on its per unit capacity. The other one will take more power. This one also will take power, but to amount contributable, the amount contributable from that machine based on its capacity. So therefore, we need to be operated like that. So this will become 150 and it will operate like that. So I think I do have, so this will back it up and operate like that. So I'll go first. I'll go thing. I think I have another example. Um, um, so in general, whenever unit get synchronized, your limiter set point goes to 100%, like that. But if some operator in your plant, if they lower the limiter set point to a lower value, so that means you are curtailing the operation. You cannot open beyond this point. So that means you are curtailing the operation of this one, like the operation line becomes like that instead of this way. So that means by bringing the limiter down, you will curtail the frequency controlling ability of that particular machine. So I know some operators, it's for them, it's easy to limit the gate and it will give a fixed megawatt, and your megawatt will be very stable with the frequency, and they will see that, or during their recording, they can write 75, 75, 75 all over the time, and it's for them, right? But in actual case, it shouldn't be the case. The megawatt should change all the time, whereas frequency should be stable. In your case, if you make the limiter down, yes, megawatt will be stayed at that point, but your frequency will take the hit. So if you can load limit like that, so that means you are limiting your capability of the governor in such a manner that the governor will not act until the frequency goes above 65. The governor will only respond or close its gate. It cannot open. It cannot basically open for a frequency drop. The frequency dropping, governor don't care because it will operate at this point. It will only be governing if the frequency becomes 60.5, which is usually do not happen. Usually the other way. Usually governor should respond for the frequency drops. It should respond for the frequency increases as well, but most of the disturbances are line tripping. And line tripping means line tripping from a generator, not from the load. So therefore, your governor will make more damage than having a governor. You don't have to have a governor for this case, right? So you need to make sure that your governor operates bearing its fair share to the system equally based on its capacity. How long? What is the time now? They passed the time already. It's actual time, right? So I will wind it up then. I think I do have some examples, but I will go through that one. Some pictures you don't need to show. And I will pass this thing. I think I already mentioned about this thing. These are like history. Yeah, I want to share with I want to share this picture. So I know that in our case, it's our practice to replace the full governor system if something goes wrong. So this is one of the example where we replace partially. Like here is an analog governor. Analog governor, you see that black boxes are the electronic cards that pushed into the card cage. See this is the one that expanded. This is the place where you have electronic card. This is the expanded view of that electronic card, and you have some relays up here. So what we did here is we manufactured a PLC based governor and ripped this plane out, and we tested this thing before the installation, because you have this panel, you tested it to make sure that everything works, and then we took 1 day outage and put it over here and commissioned the governor within a couple of days. I want to talk about detailed governors, but I think we passed our time. So this is one of the governor. I was commissioning one of the governor. So I want to talk about this thing, but I think time will not let us to do that. Yeah, okay. I want to say this thing. Like I said, when a governor operates on group, whenever you synchronize the unit will be remaining at this frequency. Then you increase set point to this load so that it will load. It will load. It will load like that. I think this is the last slide. Yeah. I'm not sure if somebody is asking questions. I can try to answer. I think it seems the time is over. Thank you very much for listening, and also thank you very much for arranging this thing. I'm more than happy to help uh, wherever, 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 whatever the area that I'm expressing. Also, not only that, I do have other people, other Sri Lankans are working over there who are uh, ex who are experienced or expertised on different areas, and I can coordinate them as well. If you do have questions, please reach us.
So please go ahead. If you have any questions, you can raise your hands as well. You can use the chat box. So are there any questions from the physical forum? So I do have a question just out of curiosity. Now, when replacing the governor, like the legacy systems, the analog governance to the digital governance, are there any main things that we have to be concerned?
You are, yeah, technically. Well, this is our basis. Whenever we look at a governance system has two parts. One is the speed controlling part, or we call it electronic part. The second part is the mechanical part. We call it force amplification, because whenever governor detects the speed error, it has to be transferred into a mechanical force that can move the wicket gates in hydro turbines, or to move to an actuator which you can use to open or close the gas valve. So that force amplification part mostly mechanical. So if that mechanical system is healthy, no wear and tear on the mechanical system, is no point of replacing the mechanical system. You leave the mechanical system alone. You only replace the electronic part, which is the part that goes obsolete faster than the mechanical system, because mechanical system you can purchase seals, you can refurbish, you can remachine, you can do lots of things to repair the mechanical system. Whereas an electrical system, in order to find an IC made in 50 years back, it's very difficult, and capacitor is very difficult to find out leak capacitor. So therefore, it's not economical to troubleshoot and repair the existing cards unless it is very simple. And not only that, nowadays, the new people coming from the universities, those are digital people. They don't know analog electronics that much. The op-amps, they don't know op-amps. So we learned op-amps and valves. Whereas the new generation, they don't even know about valves. They don't even hear about valves. So therefore, it's hard for them to, therefore, our practice is to replace the electronics in such cases. Electronics can be easily replaced with a programmable logic controller. So we use Schneider PLCs to replace those things. Usually our cost is 25,000 Canadian dollars per unit. The equipment cost plus whatever the labor to replace it, right?
Thank you very much. So I would like to open the forum. Yes. There's one question from Engineer Damita Veera Perumal. Can you briefly tell us about the virtual governor?
I think I never heard the term virtual governor, but I think he's coming from a renewable IBR background. In the IBR background, for the IBR, new IBR, they have called artificial inertia. They can create artificial energies. What is inertia? Inertia means its temporary ability to provide megawatt in a frequency event or the frequency drop. So what they do is, since it is IBR, inverter-based resources, it has its own capacitors to make the whatever the power coming in. If it is solar, it is DC, but you have a little capacitor bank, not big, little capacitor bank. So that capacitor bank, the energy stored in the capacitor bank can be released slowly instead of instant. So that those things called virtual governors or the artificial inertia. I'm not sure whether he's asking that his background is that IBR. If it is CEB, there's no virtual. I don't know anything about virtual governor, but if it is artificial inertia, I think I assume I explained the artificial inertia. I mean, artificial inertia is mostly only on the papers yet. Maybe there are a few manufacturers who has introduced it, but it's very proprietary. In IBR industry, those people will not even let you know about how they do it. I have listened. I have gone to many conferences. They are talking about this artificial inertia. Those are on the paper. Like they publish paper on artificial inertia based on modeling studies. There might be artificial inertia, but I'm not aware about particular manufacturer. But I might be wrong. My knowledge is limited on IBR.
Thank you very much, sir. There's been, I think the question has been answered. So if there's any other question, I would like to request you to go ahead, put it in the chat box. Or that we can consider there are no questions, right? Yes, okay. So let me take this opportunity to thank our resource person. It's been a great opportunity for all of us because when I saw the presentation being done to CEB engineers, I was like, I contacted Engineer Kosal and said, will we be able to ask him to do a presentation for IESL? Then the question came, like he's in Sri Lanka for a very limited number of days on vacation. So we'll try to somehow get the chance to fit in to his schedule as well as IESL schedule. So we got in touch with him and he agreed, and that's very fortunate for us because it's a very rare opportunity and we were able to quickly organize it. And I think 16th was the day the presentation was conducted to CEB, and today is 21st, just 5 days after we have done the session for IESL as well. And it's been a very insightful session, and it was very interesting to go back. Literally, I went back to my university days where we learned about these AGCs and everything on paper, in theory. But it's very nice, very interesting to see a person who is practically involved and engaged in these kind of applications, as well as we saw like how he has even been involved in upgrading the systems from analog to digital governance as well. So it's been a huge privilege, sir. I would like to take this opportunity to thank you, and this small token of appreciation that I would like to present to you. With that, you have Dr. Ravi Muthukutti's address, email address on the screen. So please contact him if you need any more further information. And we'll try to see if possible. Yeah? Yes. Yeah, in future, we'll try to see the possibility of trying to organize a CPD or some kind of like a lengthy session, which we can take more time and convert into your continuous professional development process at achievements as well. So again, I would like to take this opportunity to thank our resource person and all the participants online as well, because yes, now they have few people have left, but earlier there was around 46 participants. So it's been a very great session, and especially the physical participants, thank you for coming on a Saturday. I know it's, you have to sacrifice a lot of personal time and do it, but